All right, welcome. We're going to start off with some practice EOC questions. Here's the first one. The ones I'm going to present to you right now, they are all ones that you have seen or we've done the lessons for, so you should have a general idea of what the answer is. The first one asks us, how would a large increase in salinity of an estuary most likely affect the ecosystem of that estuary? Sorry if you hear my coffee maker in the background. Answer A says all organisms would die. B says all organisms would continue to live as they do now, so there would be no change. C says the number of salt-tolerant organisms would increase and the number of salt-intolerant organisms would decrease. And D says the number of salt-intolerant organisms would increase and the number of salt-tolerant organisms would decrease. Two of these right away we can cross off. We can do our true and false, like if we were taking a multiple choice question, you're supposed to approach each answer like a true or false. So does the answer correctly or incorrectly finish the question? A, you could cross off because not all the organisms would die because estuaries have brackish water, remember? So some organisms are able to live in that salt water because it is salty anyways. B, all organisms would continue to live as they do now. That's not true. So we could cross that one off left as well. Now all we have left is C and D. The number of salt-tolerant species would increase. If we added more salt, that would likely be what would happen, and the number of salt-intolerant species would decrease. So C here is our correct answer. I'm going to go on to another one. Which would indicate the water in a lake is not safe for drinking? So we're looking for one of our water quality indicators, and it's got to be in the negative indicator region. So A says many varieties of species in the lake. That means we have a high biodiversity. We learned that the higher the biodiversity, the healthier the water, so A is not true. B says high dissolved oxygen levels in the lake. That's not true either. We learned that high dissolved oxygen levels are good. That means that the lake is healthy, so we can cross that off. That's not true. Cold temperatures of the lake. We learned that the lower the temperature, generally the higher the dissolved oxygen. So that's not true. Dissolved oxygen is good. So we cross off C and we're left with D. Let's see if D is correct. It says high turbidity levels in the lake. That is true. We know the higher the turbidity, the worse off the water is, the less healthy or pure or clean the water is. Another one. So this one says, what best explains why all of the Earth's water is not available for human use? We've got A, most of Earth's fresh water is only in lakes. B, most of Earth's fresh water is underground. That's not true. And also we know that lakes and rivers only comprise about 1% of the available fresh water. Underground, we know that that's about 30% of the fresh water. C, most of the fresh water is still in the water cycle. That's not true. And D is our correct answer. Most of the fresh water is frozen water in ice glaciers and up there in Antarctica, or down there, not Antarctica, and up there in the Arctic. 28. If a lake has an excess level of phosphates, nitrates in its water, what will most likely result? A, the temperature of the lake will decrease. B, the turbidity levels of the lake will decrease. C, the dissolved oxygen levels in the lake will increase. Or D, the growth of algae in the lake will increase. If a lake has an excess level of phosphates and nitrates, we know that phosphates and nitrates are linked to plant growth. So does any of these have to do with plants? D does. We know that if we have more nitrates and phosphates, we will have more plant growth. So that correctly answers the question. All right, here is my bell ringer for you. So we have a cup here with fresh room temperature water. It's important to know what kind of water is in there. Let's answer the green one first. If I put really salty water into the speaker, where will it go? If I pipette it in there, it'll go to the bottom. We know that because as we increase the salinity of the water, we learned in another lecture, we are increasing the density. In contrast, if I put really hot water into the speaker, where will it go? We know that if we increase the water temperature, we're decreasing the density, so it's going to stay on top of our water. Fantastic. And here's where our notes start. So you're going to get out your ocean current notes. If you have them on the PowerPoint, that's fine. If you are a face-to-face person and you have a notebook, though, you need to be doing this in your notebook. If all you've got is the electronic version, that's fine too, although printed off notes are always the best. So we're going to learn more in depth about ocean currents. We've already talked about them a little bit. Today we're just going to talk about a couple more of those characteristics of them. It won't take us very long to do this lecture. So here we've got the ocean water column on your right hand side of the screen here. I know that we learned the ocean zones, but this has more to do with our currents and where we find our currents in the open ocean water. So on the very top part, we've got where our surface currents occur. I mean, that should hopefully make sense to you. We didn't name that tricky at all. Surface currents are found at the top of the ocean. It comprises about the upper 10% of the ocean water column, or 400 meters down. And then we've got something that we call the FICO line. That's not right. I will figure out how to say that another day. But this is, if we track the temperature, like if we put temperature down here, and this is really warm water, and this is really cold water, we would get a line that goes, and then it would tumble down when we get to the deep current. So this is characteristic because we have a rapid change in temperature, salinity, and density as we go down. So it's like all of a sudden it goes down into a steep slope. We'll look at some graphs another day about it. And then we've got the deep current section of our ocean. It's the lower 90% of the ocean. So this is not drawn to scale. Most of our ocean is where our deep currents are. And if you think about the way surface currents and deep currents move, surface currents move with more horizontal movement, and the deep currents move more with a vertical movement up and down. That makes sense as to why most of the ocean is considered the part where the deep ocean currents move, because they are moving more vertically than the surface currents. All right, this is review. Ocean currents are influenced by weather, Earth's rotation, and position of the continents. So for that one, we're mostly talking about the surface currents. Remember, surface currents are run by the wind, so if the weather changes or the Earth rotates differently, or the continents for some reason move, although they should not, the surface currents that we experience today would not be the same that we experience on that day. That's Earth environmental, never mind. And this is something that you know. We've done experiments about this, or we will do them. If you've got food coloring and time to freeze some ice and time to make some water warm, you can do an experiment. So we know that cold water is more dense, so it's going to sink to the bottom. Oftentimes cold water is saltier as well. It sinks and moves to the bottom. So hopefully you know and understand that as I increase my salinity, my density is increased. As I decrease my temperature, my density is also increased. If you look over on the right-hand side of the screen, we're talking about warm water and less salty water. As I decrease my salinity, I am decreasing my density. As I increase my temperature, I'm decreasing my density. So our warm water is more likely to be on top, and our water that is not very salty, again, is also more likely to be on top. Something we've talked about as well. We're going to do an experiment in class. You're welcome to repeat it. So you need a plastic cup or two filled with about 3/4 of water. Make sure it's clear so you can see through it. It doesn't have to be plastic. It could be glass if you wanted. You're going to need to warm up some water. You can put it in the microwave for about a minute and a half. You want it warm but not boiling because we need to pick it up. And then you're going to take that warm water and you will put some food coloring in it. It doesn't really matter what color. Red's good for effect. And color the warm water red. Then you're going to put the warm water inside the cold water and see where, or the room temperature water, and see where it goes. You can repeat this with cold water. So get a glass, put some ice cubes in it, make the water blue, and then put the blue water, just a little bit of blue water, into your room temperature clear glass, and you should be able to track where they go. Again, you can also repeat this with salt, so you can get some same temperature water, make one really, really salty, color it, and then put it in the other one, and you should see it sink down to the bottom. So you can experiment with this and see densities on your own. If you have any questions about it and you want to try it, you can email me and I can give you a lab write-up on how to do it. Or if you're at the Zoom, you'll be able to see it yourself. Okay, so I told you we have two types of currents. We have surface currents. These, again, this is all review. This is stream-like movement located at the surface of the ocean. These are generated by the wind, and the wind is generated by the Coriolis effect. So it is influenced super strongly by this Coriolis effect, the physical property or phenomenon that we see when things are spinning. So it happens on a basketball, it happens on a merry-go-round, but it also happens on the Earth because the Earth is spinning. What this looks like is currents in the northern hemisphere and the southern hemisphere. We call them gyri, or big circle currents, and they move counterclockwise in the southern hemisphere or to the left, and clockwise in the northern hemisphere or to the right. That looks like our little chart down here, right here. And you can even put in the arrows indicating which direction the water's moving. So gyri are large circular currents in the ocean. They're typically our surface currents are gyri. You can put the little, can't tell if I put the little arrows here. I don't think I did. But you can put the little arrows like this is the northern hemisphere, so we know that it's moving clockwise. And this is the southern hemisphere, so we know that it's moving counterclockwise. And please do draw in these. I put in your electronic notes for you to put the circles there for each of the gyri. We have 5 of them, debatably another one up towards the Arctic, but we don't really talk about that much. So there are 5, and actually inside each of these is a accumulation of plastic. So the one you usually talk about is the North Pacific garbage patch right here in this gyri. So because this gyri is a circling current, often stuff gets stuck here. That stuff is trash. So the largest one's right here, and it's a floating pile of trash, and they say it's about the size of Texas, but it's spread out for a while. The problem is that fish and other marine organisms are very attracted to things that are floating, especially if they're shiny things. So it's really causing havoc on the ecosystem. Plus, a lot of things are eating this, so we're finding pieces of plastic in organisms, and if you can imagine, eating plastic is not healthy for any kind of organism, so it can cause their death. We find this a lot in sea turtles. I mean, you've seen maybe perhaps sea turtles with straws up their nose, or seen trash and plastic inside the sea turtle if they died. Sometimes we do a necropsy or an animal autopsy and see why they died, but we can often find plastic inside of them. When we talk about our ocean exploration, we're going to read an article, and one of the articles is talking about how they explored the deepest part of the ocean in a submarine type thing, and they found arthropods down there, which kind of think like shrimpy things, and they found little nurdles or tiny beads of plastic inside of them. So every part of the ocean is being affected by the plastic and trash and marine debris inside that we're putting into the ocean. So it's definitely a social cause to think about, and something to start kind of getting the gears turning in your head as you start to become citizens, like adults, to think about environmentally friendly things and how we're impacting the world we live on, and mostly it's a negative way. But again, that wasn't the point of this slide. The point of this slide was to tell you that there are 5 major gyri in the oceans, and that one of them is home to a giant floating patch of garbage. Actually, most of them, but the giant one is in the northern Pacific. Most of them do have patches of garbage in them. And it can be things like stuff that you and I use, like plastic bottles and stuff. A lot of them are fishing gears and whatnot. This is a video. I'll link it on your page so that you can watch it if you want. It's all about the garbage patch. And then our deep water currents are our other kind. These are driven by density differences in the water. They're stream-like movements that are located far beneath the surface. Okay, again, we didn't label these confusing. Deep water currents are found in the deep water, way under the surface. Again, they're caused by those salinity differences and temperature differences. Salinity is the amount of water we talked about. The more salty it is, the more dense it is, and the colder the temperature, the more dense it is. So those are 2 relationships I need you to know and understand. So definitely be thinking about those. We'll go over them a little bit more, though, before we end this unit. Here is our deep water current, often called the global conveyor belt. It is circles around the world, bringing with it water and nutrients, depending on where the water is. The water is moving from down below or up above. Because again, these move more in a vertical way. This is another demo. I will link it in your Canvas page. And that's it. Have a good day, guys.